Hi everyone, we are Team 8 and we'll be presenting our analysis and redesign of dual syringe pumps. As a background to the product, syringe pumps are used to dispense controlled volumes of fluids. A motor drives a threaded rod, which is gold-colored in the model, that moves the plunger head down and up to dispense or retract fluid contained within the syringe. By controlling the motor speed, syringe pumps can accurately dose drugs, nutrients, or laboratory fluids. The product variant pictured here allows for independent control of two syringes, which is useful for mixing and diluting processes. We identified two customer segments: medical facilities such as hospitals or clinics, as well as laboratory environments. While both customers require fine fluid control, hospitals may have need for diluting and mixing medication, while laboratories may not need such mixing capabilities and may instead prefer a larger range of controllable fluid volumes. These customer demand differences are what drove the features of our product variants. Pictured here is our FAST diagram. We have one main functive branch that relates to controlling the fluid within the syringe. We can see that our function component mapping matrix identifies that many components share the role of constraining the linear motion of the syringe pump. We can also see that the syringe mount and mounting knob share all functions. These are great opportunities for part consolidation, which we will cover later in the presentation. As mentioned earlier, the two customer groups have different needs and demands. Namely, they may or may not need to control multiple fluids as well as accept larger syringes. Using the function component mapping matrix, we identified the module parts which will drive the product differences between the variants. As pictured on this slide, we can see that the different modules provide different functions to suit the different customer needs. Matching screw holes provide the common interfaces for these modules to secure to the base plate and the housing. Following the interim report, the bottom bracket was redesigned to become a platform part, allowing us to delay product differentiation. You'll see this part later in our presentation. We analyzed the assembly to find the highest impact parts on the manual assembly time. Besides the motor with its 4 mounting screws, which is a purchased part, the next top two parts were the motor mount and the housing. As we can see on the quad chart, these parts are ideal for redesign. We also selected the top bracket because we saw an opportunity for part consolidation. As we can see, the top bracket and motor mount share the same function to constrain the linear motion of the plunger, so we look to combine the two components. Starting with the housing, the original design took 55 seconds to mount it to the base plate. We improved the design for manual assembly by reducing the number of fasteners while moving it to an easily accessible location. We also added some part features to assist in orienting and aligning the part to the base plate. This had no impact on the function of the component, but does increase the overall cost due to the ledge added to the part. We were able to reduce the assembly time from 55.7 seconds to 14.8 seconds. Now moving on to the motor mount and top plate, we can see that 8 screws are required to secure the motor mounts to the top bracket, shown with the red dashed circles. These screws drove the assembly time to be 110 seconds. By consolidating these parts, we eliminated the fasteners entirely. We also made the part symmetrical so it could be flipped in either orientation during assembly. The assembly time was reduced from 110 seconds to 32 seconds. The redesign lost the holes in the top bracket for the alignment shaft, so we modified the base plate and plunger blocks to make up for the lost functionality. For automated assembly, we selected the subassembly of the bottom bracket, syringe mount, and mounting knob to improve for automated assembly. The function component mapping matrix shows that the syringe mount and mounting knob share all functives, a strong indicator for the opportunity for part consolidation. Here we can see the before design of the bottom bracket assembly. You can see that it's slightly different from the original bottom bracket, as it was modified after the interim report to become a platform part that delays differentiation. It cost $11.86 to automatically assemble. We consolidated the syringe mount and mounting knob. This eliminated the fasteners originally used to secure the assembly and reduced part variety. We made the part symmetrical to aid automatic feeding, and we added chamfers for easy insertion. We also added a feature to improve alignment for the bottom bracket. This reduced the cost from $11.68 to $4.75. These improvements had no impact on product function, but we expect a mixed impact on manufacturing cost due to cheaper plastic knobs and expensive machining for the bottom bracket.
Now let's look at the process selection for manufacturing of the housing. The main function of the housing is to protect the internal electronics. Here are the major dimensions of the housing. The manufacturing tolerance of 0.0128 inches was standard injection molding tolerances based on the current part dimensions. The most critical dimensions are the slot size and mounting hole location for the base plate to ensure it's easily mounted and secured to the housing. The housing was to be made out of ABS. Based on the size, dimension, tolerances, and batch size, we narrowed down the manufacturing processes to machining, injection molding, and compression molding. In the end, we chose to injection mold the housing. The current housing had many issues pointed out by DfM Pro. After the design for assembly changes, DfM Pro suggested to improve the rib parameters, draft angle, to modify undercuts, maintain uniform wall thicknesses, and improve the mold wall thickness. On analyzing the manufacturing cost, we calculated the operator cost to be 3 cents, the mold cost to be $1.4, and material cost to be $1.09, adding up to $2.52. We implemented the changes suggested by DfM Pro. We were able to slightly reduce the wall thickness, make sure to maintain uniform wall thickness throughout the part, add draft angles, try to avoid side pulls as much as possible, and avoid internal depressions and undercuts. On analyzing the manufacturing cost, we calculated the operator cost to be 3 cents, mold cost to be 25 cents, and material cost to be 58 cents, adding up to a total of 86 cents, saving us $1.67. These DfM changes had a slight effect on the electronics mounting that will require some changes to the electronics compartment. There was no overall effect on the assembly cost. The critical dimensions of the slot size and mounting hole location for the base plate remain the same after the DfM changes. Now let's look at the process selection for the manufacturing of the motor mount. The motor mount and the top bracket, which we combined during the design for assembly, has an important role of constraining linear motion, the most common function in the function component mapping matrix. Here are the major dimensions of the motor mount. The manufacturing tolerance selected is 0.005 inches, the standard manufacturing tolerance for 3-axis CNC machining. The critical dimensions here are the dimensions and locations of the motor mounting holes to ensure correct alignment of the motor with the syringes. The motor mount was to be made out of aluminium alloy. Based on the size and weight, dimensions, tolerance, and batch size, we narrowed down the manufacturing processes to machining and forging. In the end, we chose to machine the motor mount. The current motor mount had many issues pointed out by DfM Pro. This include the presence of long deep holes, sharp internal corners, and difficult entry and exit surfaces for holes being drilled. We also analyzed the manufacturing cost and calculated a machining cost of $9.77 and a material cost of $1.71, adding up to $11.48. With the help of the changes suggested to us by DfM Pro, we reduced the part thickness to avoid long narrow holes, stuck to standard stock dimensions. We added radiuses to internal corners and minimized tool changes and setups from 4 setups to just 2 setups. And through this, we were able to reduce the cost to $7.58, a 34% reduction based on our analytical method, and to $1.34 suggested by Hubs, a 43% reduction based on their calculations, assuming a 20% profit margin. These changes had no effect on the product function and actually improved the assembly cost due to easier assembly due to less bolts and easy tool access for the motor coupling. After making these modifications, we were still able to maintain the critical dimensions of the size and location of the motor mounting holes in order to maintain the right motor syringe alignment. Along with our product, we plan to offer services to improve customer experience and reduce the impact on the environment. We plan to use more environmentally friendly materials and handle end-of-life recycling. We also want to offer a rental option to increase shared use and provide maintenance contracts to increase the life of the product. In addition, we plan to offer data collection and optimization services to suggest maintenance whenever needed and optimize fluid delivery for better outcomes. To summarize, after redesign, we were able to significantly reduce manual assembly time of the housing and motor mount. We cut down automated assembly costs of the bottom bracket and syringe mounting system, and implemented DfM guidelines to improve manufacturability and reduce the manufacturing cost of the machine motor mount and injection molded housing. There are also a few critiques for our design. Our design changes led to a need to modify other parts such as the base plate to assist constraining the plunger. We also need to conduct additional DfM for parts we did not choose. And if we were to start all over again, we would put more emphasis on the fast diagram and function component mapping matrix earlier, as it served as a backbone for our redesign.